theory to the tool. So I'm going to, of course, as you know, I like to talk about a little bit about history, the people, and how we got there, not jump into the details. Okay, what is that? How you like it, right? What do you like about the chips? Taste or the crunchy feeling? Shape, the crunchy feeling, right? You look for the chips. If it is stale, it's not. It has to have a sound when you crunch it, right? When you taste it. So the shape of this shape is specially designed to provide maximum crunch value, maximum pressure to your teeth when you break it. That is the pleasure that they are asking for. And then they elevate that sound in the ads also, And so they choose this shape. So what is this shape called? Hyperbolic paraboloid, exactly. So this is a hyperbolic paraboloid shell. It is a true, very, very true definition of a very nice hyperbolic paraboloid shell because they are very strong due to their form. So even though the potato chip material is very weak, they just make the form in such a way that it becomes strong to crush. Okay. So now to find the best shape and the consistency and everything, they use finite element analysis to do that. One of the earlier applications of finite element analysis was to design these chips properly, right? So you can see the finite element analysis is actually quite useful even for your chip design, potato chips. Okay, and this is the equation of the hyperbolic paraboloid, and then you mesh it, and then you put it through finite element, and then you do all of that kind of stuff. So let's go to theory a little bit now. The structure like that, the one that you saw just now, potato chips or any structure is governed by, so it's a partial differential equation, and you all, people who are good in math, which I'm not, must know how to solve this one, and you have learned how to solve this one. So partial differential equations are actually the base that govern the behavior of any continuum. Continuum means that because of this partial derivative, the structure is supposed to be continuous all the time, and it applies to a small fraction of the structure at a time. It doesn't apply to the entire, so it applies to, and then you can integrate and you can do all those solutions. So that's the equation of equilibrium using partial differential equation, which links the stresses, strains, deformations, forces, everything together, right? It one go. So the problem is that for real structure, it can't be solved. You can solve it for a simply supported beam like this is fine. You can imply that, you can integrate, and you can find the solution of the displacement and the force relationship from this one, but you can't do it for a complex structure like the that we see. So that means partial differential equations are excellent tools, but they have no place in real life. They can't be used for anything useful. So the real structure is subjected to excitation and then creates a response. So excitation is a general term. That means the structure is excited by something outside, sometimes by itself. And that excitation, because we have the action-reaction thing, so the structure will respond because of that excitation, and that response is the one that we are interested to fight. So the excitation, whatever is gravity load, wind load, seismic vibration, ground settlement, thermal changes, anything that you can think of that will change the structure is called the excitation. So that's why I use the term excitation. I don't use loads, because loads is a narrow part of that. Because temperature change is also excitation. Ground settlement is also excitation. So excitation, like this one, the structure which has the geometry, topology, materials, boundary, mass distribution, 3D, 2D, whatever, doesn't matter. Everything which defines the structure and its boundaries is the structure itself. So structure itself is separate from excitation. And then when you combine the structure and the excitation, you get a response. That means structure starts to do something, and you want to measure it. Displacements, story drifts, member strains, stresses in structure, stress resultants, natural frequencies, whatever you want to measure is the response. So that's the whole system. Structural system is three parts: excitation, structure, and response. And we are always dealing with that. So What we now need is a realistic representation of the material, geometry, loads, and boundary behavior. So that is a way to represent the structure in mathematical form, because real structure is not built. So you cannot get the response unless you test it. So if you want to get the response before you build it, you need to have a mathematical model of the structure. And then once you have that, we need procedures, methods to solve this mathematics, because mathematics we may have, but the mathematical model will be very complicated. So then we need some tools to solve that mathematical problem, because traditional mathematical solution, I told you, will not be suitable for this kind of solution. So then we can find what is the structure as a response. So that's the problem here. We need two things. We need, first of all, a way to represent the real structure reliably, realistically in a mathematical model. Done. Then we need a tool to solve that mathematical model so we can get the response out. So those are the two very different problems. One is called modeling, one is called analysis. So the step to convert the structure into a mathematical form suitable for solution is modeling, and then solve that model to get the response is the second step. So we're trying to now solve two things at the same time. Okay, so that means, first of all, the first thing we will do is we will convert the structure into mathematical simpler form. So this structure will become a spring, because the same thing. Spring is the same thing. You have a structure, you apply a force, you get the displacement. Exactly the same what is happening here. So let's start with the spring, because spring is easy to understand. So if we can solve the equation of a spring, which we already know how to do now, because thanks to Hooke's law long time ago, that means we already have a way to solve the mathematical model. As long as we can convert the structure into a spring, equivalent spring or spring-like thing, then we already have the solution, right? So the job is done. So now the question is, how do you convert a large complex model into a spring? And what kind of spring will it be? What kind of properties will it have? What kind of response will it have? We already studied most of it in the last part. So that's the excitation, that's the response, and we get the system. So now these two things are the same. One is a pure mathematical, second one is a representative mathematics. So that means we can use the classical solution using partial differential equations, go through some magic or gimmick, which Dr. Krishna taught you how to do that, I'm quite sure, to convert that into an equivalent structural model equation, which is this one, KR into R, or something like that. So we converted the classical partial differential equation using the principle of assumption, equilibrium, stress strain law, compatibility, using the principle of virtual work, all of those things, which I don't remember now, to this one. All I'm concerned is that now we have this. Of course, I used to do all of that at some point, but I'm sure you. So the thing is that we know how to do that now, which is what is called the finite element. So we now have a structure, F, K, and delta, same as a spring. So basically, structure is no more than a big spring. So any structure, no matter what it is, for us is a big spring, is a complex big spring, right? So that means the solution is known. Now it's just a matter of doing the hard stuff of how complicated the spring is, how to calculate its stiffness, what is the mass, all of that thing. So that's the reality, that we go from this one to this one. So then we come back to this equation, that this equation we developed that one, this one here, but we found that this equation is not enough, because we have loading which could be static or dynamic. We have material which could be elastic or inelastic. We have this geometry which could be linear or non-linear. So which means that spring is more complicated than that simple spring. And luckily, we already have equation for that also. Last time we talked about that. So that means we have the equation where external force, mass acceleration, damping velocity, stiffness, displacement, and nonlinearity. And we put the capital M, which is that this is the sum of all of the masses in the structure. This is sum of all the damping in the structure. This is sum of all the stiffness in the structure. This is sum of all the forces applied. Sum, I mean accumulation. Let's say accumulation, not sum, which is a matrix or a vector. So we put everything together into one big matrix or a vector, not missing anything at all, and then put them together as one set. And we'd say, okay, now we have the equation. It's just a little bit too big, fine. And we can't solve it because now there is no single number to achieve, which means that we need computers to do that for us. So finite element basically is to do that from there to this one and then to solve it. So A, we need a real structure, cannot be analyzed. First, these statements are the basis. Please never forget them. A lot of people say, I'm analyzing my structure. After this class, don't ever say that you're going to analyze your building. You will say, I'm going to analyze the model of my building. As soon as you say that, you will realize that your building and your model are different. So your response is not for the building, but for the model. If your model is bad, your response is bad, even if you use the best computer program in the world. Because your model doesn't represent the real structure. So your response doesn't represent the real structure also. So as soon as you start thinking in terms of the difference between real structure cannot be analyzed, period. If you want to get the response of the real structure, what do you do? What do you do? Test it. Basically test it. Structural modeling is fine. Can same thing. Measure it. Test it. You can't do it before the structure is built. What we are trying to do is we are trying to do something about a structure which does not exist at this time. That means we are only working on the model of the structure. So please keep this, never forget that you are always working with the model of a structure, and your response, your results, everything is just as good as your model. Nothing better than that. So once we have that model, we can only analyze a model of the structure. And we therefore need tools to model and analyze the structure. So we need two tools now. One tool to model and one tool to analyze that model. Two separate tools. Although they are often considered the same, but we have to think of them as two separate tools combined together. To get the real response, real structure must be tested. You have all done that. And that's why we did that last time, that you get the feel of the real structure of breaking and cracking and measuring and try to correlate with your simple. And we tested the most simple structure there is, simply supported beam, right? And we broke it. It's no longer there, so you can't use it. So which means that we know now the value of the real test and the results that we could get. And all the mistakes that you made. In this structure also we made a mistake. The two displacements were not equal. I look at it and I thought you guys did a good job, but actually not. So many issues still there because somehow we didn't get the perfect response as we expected. Okay. So, but your model always gives you nice results. Your model was saying, this is a fixed support, so I will get equal reaction here. But in reality, they were not equal because you made some inequalities there. So that means the real response varied from your model right away, even if it was controlled lab environment. Imagine how different the real response of a real structure where the workers are working in a heat, at night, who have no idea of what you wanted them to do. They're just doing some work, right? And we are trying to correlate that sophisticated ETABS screen with what's happening in the field. So please remember that this is the difference between real structure, real testing, real response, model of the structure, and analysis of a model. Okay, coming back. So we need to cover the complicated structure by a simplified rectangle, which means that we have to simplify it so it can fit our modeling tools. Depending upon what tool you have, your model will have to suit that tool. If your program only has 2D analysis, you have to convert your complex structure into 2D frames, which we used to do before. We never had 3D. Actually, we didn't have any program. But when we had the first one, it was 2D from AIT called Microfiche P1 and P2. So, which means that the tool now becomes the primary decision maker of what your model will have. So you are limited now by the tool that you will get. So you have to adjust if you're using ANSYS, okay, fine, you can do a lot. But can you do a real structure in ANSYS? Maybe in a couple of years, but not so quickly, right? So that's the problem. This box is the key. How tightly this box fits the real structure. If it is ANSYS, maybe you can make the structure the box exactly like the structure, almost close to that one, because ANSYS has that much power in it. But if it is frame 2D, like from eagle eye, you will have to convert that structure into a 2D frame. So that's the first step. Then excitation has to be simplified. Then response has to be simplified, depending upon the model. Because if it's 2D, you get just few forces. If it is ANSYS, you get a trillion numbers, right? So what to do with those numbers is a different story. And how to put all the data is a different story. So geometry, materials, boundary, and loading. These are your 4 modeling decisions, which will change everything. First of all, geometry. How much geometry are you going to model consider in the model? Are you going to put every opening, every small cantilever, every brick? Are you going to put every window, every door, every light bulb? You're saying no, yes, but some people will. Some people can. They need to, depending upon what you're doing. So the decisions on geometry will decide what is going to represent your structure. Material is another one. We already talked about in the first course about this one, complexity of materials, right? So many, isotropic, orthotropic, linear, nonlinear, elastic, inelastic, all kind of things. But in program, you may only have E value to input. So everything will be condensed into an E value for a material. So that means material modeling will be the second problem. How much modeling of the material are you going to do? Ductility, confinement, temperature, all you put that, aging, so many things. Where are you going to draw the line for the materials? So once you make the decision about the geometry, then you have to make the material about materials. Then boundary. How well can you represent the boundary? This is the way where people do the most, I would say, inaccurate and bad decisions. Complicated structure, very detailed, and at the foundation level, pin and fix support. They cannot see the foundations, they cannot see the soil, they cannot see the piles, they cannot see nothing. They just stop the building column, like this one, and here they put a line, and then this is my pin support or revision. So they completely eliminate the boundary from the model and represent it by a most simple, inaccurate manner. So boundary modeling is often the worst in all of the errors that we make, because we never model the boundary as it should be modeled. Then the loads and excitation. Oh, that's another story altogether. We simplify the load so much. As I told you, wind is so complicated, you convert that into a pressure. Earthquake, we don't do time history analysis, we convert that into a lateral load or time or response spectrum at best. Same thing with every load. So, which means that we simplify the loads a lot, we simplify the boundary very much, materials, geometry. Now you can realize how far your model is from your real structure, even if you use ETABS or SAP, top tools in the field. You are still so far from the real structure. The performance-based design tries to bring you closer, but not close enough. So don't say that performance-based design is the response of it's a very good response of a model, nothing more than that. But do not relate it to real structure. Okay, so let's step back a little bit. Why do we need the analysis in the first place? We're talking about analysis. Let's step back and see, why do we need the analysis? We need the analysis. Okay, if I go back to the slide, you already read it. I don't know how many people read it. Why do we need the analysis? It's the second step which is which is important, not the first step. The first step is just a way to get there. And if I can get to the second step without analysis, I'm perfectly fine. I don't have to do the analysis. And that's what we used to do. You know, all the buildings built before 1975 or 1980 are built without analysis. The Eiffel Tower, I mean, hand calculation, not the kind of analysis that we are talking about. Empire State Building, 100-story building, by hand. No, none of this existed. No tools existed. So which means that if somebody could design it by whatever way, is fine. All you want to do is design. What does it mean, design? We are worried about the response. We are not worried about the forces. We are not worried about anything. I told you a long time ago, we are worried about the response of the structure. Acceleration, remember, it's a response. That's what we are worried about. Falling down, stability, displacement, these are responses, not forces. So our worry is, real worry is the response of the structure, especially the deformation response of the structure. That's what we are worried about. We are checking the drifts. We are checking the rotations. We are checking the deflections. We are checking the accelerations. These are the ones that we are, all are derivatives of displacement. So we are basically worried about the structure not becoming a car or automobile running away. It must stay where it is. It is supposed to be a stable, stationary system. That's what we are worried about. Mechanical people, electrical people, car design people don't worry about car standing. They worry about how fast it can go, how well it can move. Totally different objectives. So we are worried about controlling primarily the displacement related responses. And everything else falls into place because of that. So that's the thing. So that's why we can ensure that the structure can sustain the excitation with an acceptable level of response. So we have three systems: structure, excitation, response. So we are saying that the response, whatever response we choose, must be acceptable for the excitation on the structure. That's the definition of why we need this. That's the design. To calculate the excitation, we need to go to analysis. To find out whether the excitation is acceptable or not, we go to design. If it is not acceptable, we go back to change something in the structure, which is called the design. Making the alteration in the structure so that response comes back to the limit. That's it. That's design. Always we are trying to find the structure that will have a response for a given excitation. Calculate putting big member sizes, putting a damper, putting reinforcement are all part of those decisions. This is the overall process I showed you before also. You start with the conceptual design, architectural, functional, then we develop the structural system, which you already have, we have learned about that. Then trial section, we start with something initial, we do the modeling because modeling requires this, then we do the analysis, then we go to the member design, we check something, revise section, go back in the cycle until we are satisfied that's okay, then we go and connection design, detailing, and final design. So that's how we carry out the system. So we have a loop here which ensures that the response will be acceptable. We cannot go outside this loop until it says acceptable response. So do we now understand completely why we need modeling, why we need analysis, what is design, how important is modeling, how approximate the model can be, and so on. So coming back to this one, so excitation is loads, gravity, wind, earthquake, vibration, settlement, temperature changes. We apply to the structure, which is K, that is F. This is delta, displacement, strain, stresses, stress resultants, internal force, axial force, shear moment, then go to design, and then go back there if needed. So that's the full story of what we are doing. And now we are entering the part where we are going to create this model, we are going to apply this loading, we are going to get the response, we are going to check the design. We have already, all the theory is now in place. Now it's the time for applying that to your project and to the real work. So please now go to the next step of creating a detailed model in ETABS. This is now about, we are starting that part. I know you already know how to use ETABS, but that's the thing. I keep saying in many conferences also, don't become a ETABS operator and say that I'm a tall building designer. That's a confusion many people have, that because I can operate ETABS, people write on their resume, I'm an ETABS operator, or I have a skill, ETABS. That's fine, it's a skill, it's a tool, but that's not what will make you a tall building designer. It's the part of all of the understanding behind that. And that's where most of the time should be spent. Okay, all right. Human heart, brain, skull, teeth, aircraft, potato chips, tower, building, dam, stadiums, it doesn't matter. Finite element is equally applicable to all of these things. So finite element method at the root has no understanding of the problem that you are trying to solve, because it's a mathematical equation of relating the something with something. So people can use it for air quality control check, water seepage into the water, whatever, designing fabrics, jeans, all of that, people can use it because the mathematics behind that, everything is the same. Or every physical system, irrespective of what it is, has the same mathematical formulation. We are just one of that. Okay. So finite element method is a discretized solution to continuum problem using finite element analysis and finite element. So this slide is very, very important. And I want you to spend some time on it, because this is where people get a lot confused. And they use these two terms often in the wrong way. So let's separate the tool from the method. So finite element analysis is a tool, and finite element method is the math used in the tool. So this is a mathematical way to convert a partial differential equation into a numerical arithmetic algebraic equation. Converting from the equation that I showed you earlier, that partial differential equation, into KR equation, that is part of the finite element method itself. So finite element method, when it was invented, they found a way to convert a partial differential equation into an equation that can be solved by pure numbers, taking the math out, because computers came up and they saw opportunity to do this. So they found that, but at that time, they don't know what it is going to be used for. Mathematics people found a nice way to solve a partial differential equation using numerical techniques. That was the paper. It had no vision, no idea how it will be used. The people who did that, first time it was published, it was just a paper saying that, oh, I can solve the partial differential equation using a numerical method. Then other people came in and said, oh, really? That's nice. I can use it for this. I can use it for that. I can use it for that. Somebody said, I can put it in a program. Then the whole thing started. And then the finite element analysis was built upon the finite element method, which was developed obviously first, and finite element analysis followed from there. So what you people use, what we use, is FEA, not FEM. FEM is embedded in the code of the ETABS or SAP solvers. Even they don't use FEM in that. They do shape function and things like that, but it's mostly developed. The development in FEM has stopped maybe like 20 years ago. It's just the same. It used to be 25 years ago. Nothing new has happened. There's a lot to do, but it's happening, but not at the same rate. So that's why both of these, FEA and FEM, can solve all these problems. So if you talk to a mechanical engineer or even these guys, I remember when you were growing up, they said, you want to be a doctor or you want to be an engineer? If you want to be an engineer, you should study math. If you want to be a doctor, you should study biology. But actually, doctors use math more than we do, because here their model of the finite element model of the heart is so complex. If I ask you, can you create a finite element model of a human heart in SAP 2000? Will you be able to do that? Not a finger. I ask you to model this finger, you cannot, but people do. I told you the story about the dentist, right? So when I went to that and said, I'm going to put a bridge on your teeth, I said, yeah. And then he explained all the things. And then he showed me the finite element analysis of the bridge, of the tooth bridge that he was going to put, in implant. So the implant is designed by using finite element method, and the stresses in the bridge, that resides on that one, are calculated. We can't do it, I'm sure. And we claim to be, the experts in FEA and, engineers. But talk to the doctors, talk to the dentist, talk to the people who design all these fabrics. The wrinkles on the fabric are computed beforehand by finite element analysis to see which fabric will fall nicely. Can you do it? We are stuck with the very basics, E and I. Nobody knows, nobody talks about E and I, modulus of, this moment of inertia thing. line element. Doctors and mechanical engineers don't know what's a line element. They only know solid element, the reality. It's we that we are so behind. We are the one who develop engineers, but we fall so behind now. Anyway, so that's this story, because we somehow did not evolve as others have in application of this one. So that's why let's look at the historical context more a little bit now. Okay, these are the people, the names that you should know. I'm sure you know. Fine. So start with this one. He started the underpinnings of the FEM 43, first mathematical stuff, how to do that. Then 1960, this guy normally say this is finite element method. He put the name on that one, Ray Clough. So he is normally credited with creating finite element method. And then metric stiffness method, Turner, Clough, they together that one. And they, in the Boeing, so the aircraft industry got interested very quickly because they want to design the wings. They took it up, and then they supported some grant, and they developed this method in 1956. And then we have this guy, Zienkiewicz, did the best work on finite element formulation of elements and development and all. So I don't know if you have studied his book or you have not. I did when I was doing masters. So his book is very, very comprehensive and really, really good material. So the point is that these are the few people who worked on the finite element method itself, not on the analysis. So that we have to separate two groups: people who worked on developing the method, and then people who took the method and start developing software, which is the finite element analysis. And that is the second group. These 4, 5, 6 people, of course more, but we are just showing you this one. So 1970s, SAP was introduced first, then SAP IV. So this one done by Edward Wilson, and then Bathe, which is in MIT, they collaborated to create SAP IV and make it open source. They gave this code to everyone. Open source means they published the code and then distributed the punch cards. It was in punch cards, of course, right? Not on GitHub or anything like that, just punch cards. So people would carry the punch cards with them, like this one. That's the code. Made it, and then every university had that at that time. Mostly universities had it on mainframes. And then ETABS was started with Wilson and him, and then SAP 2000 and ETABS came up, then Perform 3D by him, and then Perform 3D go to ETABS and CSI. So basically CSI primarily took the main leadership in finite element analysis tools. And the reason is that he's from Berkeley, and he's also, so most of these people are from the same university. Most of the research was done in Berkeley. So that group becomes stronger. So everybody joined the same group and they lead. Okay. And of course, now we are working with the same group and we are developing software with them, as you know. So these are, you can say, 4. So Perform 3D, performance-based design primarily started by this guy, application, by his program. Nonlinear analysis, nonlinear modeling, he's the guy. And SAP 4, the original one, he's the guy. ETABS and SAP 90 and later, he's the guy. And of course, his company took over 50 years ago. Right? So that's the two sides of the story. Okay, these are very important statements made by two people, and please absorb them deeply because these are the people who are involved in this one. So he said, engineering is the art of modeling materials we do not wholly understand. I told you, right? We don't know the material actually. It's an art of modeling them, approximating them. Into shapes we cannot precisely analyze. Complex, we convert them back to models. So as to withstand forces we cannot precisely assess. We don't know earthquake, we don't know, we just also make a lot of assumptions and simplification there in such a way that the public has no reason to suspect the extent of our ignorance. They don't know how much we don't know. Really, if the public know that we make so many approximations, and so many simplification to their structure, they would not trust us because other engineers are not doing like that. So we are probably the last engineering community left. No, people are behind us even more. So who really make things very simple still, despite all of the advancements. And then this one, same. Structural engineering is the art of using materials that have properties which can only be estimated to build real structures that can only be approximately analyzed to withstand forces that are not accurately known, so that our responsibility with respect to public safety is satisfied. Similar thing, that we are doing something, we honestly don't know what we are doing. That's why I told you the story that long time ago when I started my practice and a guy came to me, can you sign a certificate saying that the structure you designed is safe? And I'm reluctant to sign it because honestly, I don't know if it's safe or not. All I did was follow what I'm told. But I said, no, I cannot sign this. I can only sign that I follow the code. He said, I don't care about your code. I hired you. I need certificate from you. And because we don't really know enough about what we have done. We know how much we haven't done. Anyway, so that's the whole thing behind all of that.